Let's start. Welcome to the EPSRC Center for Doctoral Training Agriforwards CDT seminar series. Today we will have Rebecca Ward. Rebecca Ward is an expert in energy modeling and simulations, in particular for urban infrastructure like buildings. And she has worked in a number of projects on energy modeling in buildings, and this is particularly relevant for a number of topics that are very important at the moment, like reduce carbon emission, or, for example, to understand how to improve the performances of growing inside. So, for example, she is interested in crop growth in underground structure or in building, and for doing that, it's very important to understand what's going on, to model, to simulate, and to optimize essentially the performances of the system. I had personal experience of working with Rebecca, which has been great so far. I'm learning a lot from her experience, her modeling approach, and so on and so forth. And today, the talk of today will be really at the cross road between energy modeling and building, and the particular specific domain of agriculture and growing indoors. So without any further delay, I'm happy to leave the words. Oh no, before we go to there, let me also remember that we have another, I'm very sorry. This is the bio of Rebecca. I should have switched on this slide much more earlier than now. And so this is Rebecca, and there will be another seminar, the 18th of June, Elliot Dixon, that will discuss with us about data and automation lead from Agri-Epi Center. So please stay tuned for the next seminar. Back to Rebecca. Thank you very much for joining us, Rebecca, and please, the floor is yours.
Brilliant. Okay, so I just need to share my screen. Hang on. Share screen. Okay, you see my slides, hopefully. Okay, thank you. Thank you, Fulvio. Thank you for the introduction. Yes, my name's Rebecca Ward, and I'm part of a team working on agriculture in buildings and in the urban environment. So I came to Cambridge about 10 years ago, actually, and I came on a Daphne Jackson Trust Fellowship, which is a returners fellowship, to work on a specific project with the Royal Botanic Gardens at Kew. Now, I'm an engineer by training, and I'm interested, as Fulvio said, in energy in buildings. And the project at Kew was very much looking at the ornamental glass houses, and what they wanted to know was what they could do to their glass houses to actually reduce the energy consumption. And bearing in mind these are listed buildings, there's very little they could do in terms of changing the appearance of the buildings. So we did some simulation work to actually look at what they could improve in the building fabric without changing the appearance to actually improve their energy demand. And as I say, that was about 10 years ago, and one thing led to another. And since then, we've worked on protected horticulture with APS salads. We've moved into urban integrated agriculture and building integrated agriculture, which are really what we're really interested in, because these basically take our understanding of buildings, which is where we're coming from. And my team are into energy and buildings, and my supervisor is an architect by training. But it incorporates also the knowledge of plant simulation that we learnt very much through the Kew project. So why are we interested in this? Well, our cities, I don't think it's too much to say, our cities are under pressure. There's increasing population growth, there's increasing people moving into cities, although with the past 12 months, there may now be an increase of people moving out of cities. And either way, we either have a lot of people in a small space, or we have a lot of empty space within buildings. So either way, our cities are under pressure. We're interested very much in the energy consumption and bringing that energy consumption down. But in a city, there are other issues as well. There's food security. If we've got an increasing population, we need to be able to feed everybody. Food miles. We want to be able to feed everybody, but we want to keep the impact of that food down. And health and well-being. I think we've all found over the past 12 months that access to green space, whether it's indoors or outdoors, helps our health and well-being. So our question is, can urban integrated agriculture provide a common solution? And if not a solution, can it at least help? Can it make things a little bit better? So there's different types of typology of urban integrated agriculture. The first one, standalone, is what it says really. So plant factories, or these shipping container type mini farms. And the point about this is that they don't interact with their environment very much. They're very much closed systems. The next typology we tend to call urban integrated, which is where you have a farm that may be on a rooftop, or it may be underground, or it's in a space within the building, but the air is not coupled with the rest of the air of the building. So it's not having any impact directly on the rest of the building space. And then the third typology is the building integrated typology, where you have a fully coupled system. So you have plants in your buildings, but the air is actually passing through the spaces occupied by the plants and the spaces occupied by the people. So the system's fully coupled. So what do plants do? Now, I know I'm preaching to the converted here. I know you all know what plants do. So they transpire and they photosynthesize. But as engineers, what we want to know is, okay, what's the impact of that on the space that they're in? As regards transpiration, the impact is typically a cooling and an increase of moisture content of the air. For photosynthesis, the impact might be a net removal of carbon dioxide and addition of oxygen, provided the growing conditions are satisfactory. And also, if the plants are inside a building, then you also have heat and mass exchange between the plants and the growing medium and the rest of the building. So all of this needs to be taken into consideration. And so the question is, can we quantify these effects? For transpiration, we use the Penman-Monteith big leaf equation. So this isn't anything new. This is quite an old equation now. It treats the crop as a single big leaf, and it calculates the heat loss from the transpiration as a function of the difference between the moisture content at the leaf surface and the moisture content of the air, factored in by this resistance term, which is dependent on the crop you're looking at. Again, photosynthesis, it's not a new equation. This has been taken from the literature, and it equates the gross photosynthesis rate as a function of the CO2 concentration in the stomata, the CO2 concentration point, compensation point, and the canopy electron transport rate, and a similar equation for the photorespiration rate. And so we have some equations, and so we can put some numbers to these equations. So if we think about a typical office, we might have a lighting level of 500 lux, that's fairly standard, temperature of 24 degrees, relative humidity 50%, and let's assume we've got plants with a leaf area index of 3. That's not enough, we need to make some more assumptions. We can assume that the lux is all photosynthetically active radiation. We can assume a CO2 level. We can make some assumptions as to the plants and their stomatal resistance levels. And from the equations, we can calculate air moisture content, Ca, the moisture content at the surface of the leaf, assuming it's a couple of degrees cooler. We can use the equations to calculate our stomatal CO2 concentration and these values. And then we can use the equations on the previous 2 slides to give us an estimate of what the plant's impact is going to be. And it gives us, these numbers give us a heat loss of 90 to 180 watts per square meter, a moisture contribution of 0.04 to 0.08 grams of water per second per square meter, and a net photosynthesis rate. So that's removal of CO2 of 4 milligrams per second per square meter. So that's quite nice. And in an office, we have people, obviously. So we can actually look at what a person would contribute. So in building energy simulation, for a person, we tend to assume in an office a heat gain of 130 watts per person, and a moisture contribution of 0.01 grams, and a CO2 input of 8 to 12 milligrams per second per person. And so actually, if you compare these numbers, it's fairly straightforward to see that if you've got 1 to 1.5 square meters of planting with a leaf area index of 3, you're approximately counteracting the heat input and the CO2 input from a single person, but you're adding quite a lot more moisture. So that's something that's really key, that if you're going to put plants into your office, you need to have some means of dealing with the additional moisture contribution that you will get. So yes, we can quantify these effects, but I've put approximately there because there are a lot of assumptions in this, and it is very much an approximation. So we've put these sorts of equations together into what we call the greenhouse energy simulator package. It's a physics-based model of a 1D slice through a typical greenhouse. We didn't write this from scratch. We actually based it on an existing model, the GDGCM, and which was originally written in Fortran. And so about 10 years ago, we took that Fortran code and we translated it into MATLAB because that's what we were more happy to work with. It's a lumped parameter model, which basically means we treat all the plants as a single node and the growing medium as another node and the tray as another node. And we look at heat and mass transfer between those nodes, where we've calculated the transfer coefficients based on the actual geometry. So although it's lumped, we've actually used the actual geometry to calculate what the model does. And then we have boundary conditions coming in from the outside. So as I said, we solved the heat, mass and carbon dioxide balance equations. And if you're interested in this particular model, there is a version on GitHub, which gives this little typical greenhouse as an example. Okay, so let's move to the urban integrated situation. And we've been really fortunate over the past probably 7 or 8 years at least to be working with growing underground. This is a farm which is in Clapham in South London. It's 33 metres underground. It's built in disused World War II air raid shelters. Now, these tunnels were built, they're at round about the same level as the London Underground system in Clapham North. The idea, I think, at the time was that they would build these tunnels, and then after the war, they would actually subsume them into the London Underground system. But basically, that never happened. So they sat there disused ever since the war, pretty much. They were used, I think, for storage for a little bit and to house the Windrush immigrants as well. But basically, they really had very little use. So they looked, when we first got in touch with Growing Underground, they looked very much like this. And at the time we first got in touch with them, there was literally a couple of benches down the bottom of one of these tunnels with a couple of grow lights and a plastic sheeting covering off the entrance. So when you entered the tunnel, all you could see was this kind of pink light down the bottom of the tunnel. But it's progressed sort of over the years to look like this, which is fantastic, actually. It's a fully operational farm. They grow microgreens and baby leaf salads. They produce, in comparison with a traditional greenhouse, they produce 16 times the crop weight per unit area. And they use 4 times the energy consumption compared against a traditional greenhouse. So it's very efficient use of space and an efficient use of energy as well, even though obviously there's no solar radiation coming in. So all of the light coming in has to be provided from the grow lights. They were winners of the Future Food Award in the BBC Radio 4 Food and Farming Awards in 2017. And as of March this year, they're a certified carbon neutral plus organisation. So they really are a fantastic future looking organisation to work with. So over the years we've been involved with them, one of the main things we've been doing is actually collecting data. And now we're really lucky to be in the position where we've got a whole load of sensors down there that are recording data and are transmitting that remotely, so we have remote access to it. When we started, we went in, when they first set up the operational farm, we went in and put in some temperature, relative humidity and CO2 sensors. And at the time, that literally involved us going and laying Ethernet cable from the ground level down to the tunnel 33 meters below, down the lift shaft, because there was no Wi-Fi in the tunnel, so no internet connection. So we basically had to do that, it was quite a challenge. But fortunately, over the past few years, my colleague Melanie has done a fantastic job of really getting to grips with the monitoring, putting a lot more monitors in. Growing Underground themselves have put Wi-Fi down in the tunnels. So the whole system has come up and is running and is producing a lot of data now, which is brilliant. We also have, in addition to the remote sensors, the sensors that we can access remotely, we have a whole load of local temperature sensors, which we can move around very easily. The only issue is you have to actually physically go in and download the data. And then there's manually collected data as well for water use and energy use, and manually collected data that isn't metered for operational conditions. So such things as the state, whether they've opened or closed the doors, for example, and the settings on the ventilation system. And crop data, obviously this is really important. So the harvest yields, the dates of plants being put into the farm from the having germinated, and all that sort of information. And then we also have access to external weather data. So one of the things we've been doing with this is we're developing a digital twin. And this is in conjunction with the team at the Alan Turing Institute. And at the moment, what we have, and I'm hoping you can see this video, is a visualization platform. And this will be developed over time to include the models that we've developed, so that the models are running using live stream data to create a fully fledged digital twin. So at the moment, the visualization platform looks like this. And you can see it shows the tunnels, the lift shaft coming down, and the tunnel where the plants are growing, and there's sort of an image of the trays. Each of the little hexagonal points is a sensor, and when you click on the sensor, it will tell you what the temperature, relative humidity, and CO2 levels are. It's also been put into context, so it's actually been put into a sort of representation of the cityscape. So you can see here's the farm tunnel, and there's a parallel tunnel running alongside it. And you can see it, obviously it's spinning around, but you can see how it's located in and around the urban landscape. And we'll be able to do things like do nice, pretty contour plots that will be able to show what's going on in the farm at any time. So that's a fantastic resource now. So we've got this visualization of the data. And as I say, my colleague Melanie has been doing a brilliant job taking all that data and doing a lot of statistical modeling with it and generating forecast models. But at the same time, we've actually got this physics-based model. So we took our greenhouse energy simulator for a standard greenhouse, and we've adapted it for the growing underground environment. Now, the first thing, obviously, there's no solar radiation, so those equations come out of the system. But instead, we've got the lights, heat coming from the lights, and the photosynthetically active radiation coming from the lights. We have heat loss to the surrounding soil that needs to be put in. And we have a change of crop. Whereas at Kew, we were looking at tropical plants, APS salads, we were looking at tomatoes. Now we're looking at microgreens, for which there's been very little research done. So we've used resistance equations based on lettuce and taken from the paper by Luc Gramans. The model obviously needs boundary conditions and parameters. So boundary conditions, we have the weather, closest weather station at the time was St. James's Park. We have an estimate of the deep soil temperature. So that's the soil temperature around the tunnel and the temperature of the lower chamber. The tunnels are circular, but there's a floor inserted, and the farm is in the upper tunnel, and the lower tunnel is used to store water for the irrigation system. We also need material parameters for all constituent materials. We need the operational conditions, so what's actually how the farm is being operated, when the lights are turned on, what the ventilation rates are, all that sort of thing. And obviously we need plant parameters, thermal properties and crop growth and photosynthetic parameters. Okay, so the model gives us, what it does is it solves the heat and mass balance equations and calculates temperature and air moisture content for the different layers of the farm. Obviously of interest is the air temperature, and this top plot on the left shows you the air temperature as a function of time over a period of about 18 months. The black solid line is the external weather, so that's the temperature of the air that's going in. And the pale blue line is our predicted temperature from the model, and that matches up with 2 periods of monitored data, the red and the pink, for this particular period of time. You can see actually that the outdoor temperature has a much higher seasonal variation than the indoor temperature. And that's one of the nice things about growing in the tunnel underground, is that the temperature of the ground down at that level is much more stable over the year than it is at ground level. By comparison, the air moisture content is actually much more closely linked to the air moisture content of the air that's coming in, as you might expect. So the ventilation air is coming in from the outside, and it has a certain level of air moisture content. So what we can do with this model is we can plot these results in a slightly different way. And this is quite a nice illustration. So on the right hand side here, we have temperature plotted, internal temperature of the farm plotted as a function of the external temperature. The blue is our simulation output when the lights are switched off, and the red is the simulation when the lights are switched on. So immediately you can see how much heat input the lights are giving. The green and the pink are the corresponding monitored data points. So green for the lights off and pink for the lights on. And you can see that our model would predict that as the external temperature goes quite low, down to 10 degrees C and lower, we would predict that the internal temperature in the farm would equally go very, very low. But you can see from the monitored data that that's not happening. And the reason is very clear. It's that the farm operatives are they're actively managing the farm so this doesn't happen, because they really don't want this to happen because the plants will stop growing. So they're doing things like altering the settings on the ventilation system, or they're shutting the doors, or they're genuinely actively managing things. And that's great, and it obviously makes the plants grow and they get their crop, but that's actually very difficult to simulate because we don't actually know they're doing that. So why is a physics-based model useful? I mean, you might say quite legitimately, you have lots of monitored data now. You can run statistical models, you can generate forecasting models, and my colleague Melanie has indeed done that. So why do you need a physics-based model? Well, a little example here. These plots show you the hours of the day that the temperature is in a certain regime in the farm as a result of our modeling. The black line is the external temperature going in. So if it's blue, it's too cold. If it's green, it's an acceptable temperature. And if it's red, it's too hot. And on the left-hand side, we have what happens if you put the lights on overnight. So remember, we're 33 meters underground. The plants don't know whether it's day outside or not. So it doesn't matter what time you put your lights on. And the lights generate not just light, they generate heat. So in the winter, it doesn't make any difference whether you put the lights on at night or the lights on in the daytime. You're still going to be too cold for certain periods of the time, unless, as I say, actively managed. But in the summer, if you put the lights on at night, you have far fewer hours when it's too hot and far fewer hours when it's too cold than if you put the lights on in the daytime. Now, this is not, it's quite intuitive, because obviously at nighttime it's colder, so you're putting the lights on in the farm when colder air is coming in. So you're effectively buffering the temperature in the farm. By comparison, if you put the lights on in the daytime when it's got warmer air coming in, you are going to overheat. And if you cool down at night when there's cold air coming in, it's going to get too cold. So it's very clear that this is what you can do with the model, and it can be used for scenario evaluation. Whereas practically, the farm is it's a concern. They're trying to make a profit. They don't want to be running different simulations different experiments like this practically, because they just, they don't have time to do it. Whereas we can actually run the model and we can put lights on for 18 hours a day or 12 hours a day, and we can actually analyze the difference. So this is really useful use for the model. Can also be used to quantify the impact of uncertainty in the model parameters. So for example, we've assumed that the deep soil temperature is 14 degrees centigrade, but we can actually change it in the model and see if we've got that wrong, what's the impact? And you can use the model to provide information about parameters you can't actually measure. So for example, we can't measure very easily transpiration rates on these crops because they're so small. But what we can do is we can infer, if we can get our model to match the data, we can actually infer from the parameters we're putting in the model how much impact that transpiration rate has on the model, but also what sort of transpiration rates we think we have. But when does a physics-based model fall down? Now, any model you need to calibrate to ensure that the model adequately represents reality. Now in this plot, it's showing relative humidity, and the black solid line is our simulation output, and the blue dots are measured data. And you can see that for this period in the summer, in July, August and June, we're actually getting pretty good agreement between the model and the data. And the reason for that is we've actually calibrated the model over that period. But as soon as you move away from that period, you move into the winter, then the model doesn't match the data very well at all. And this is actually quite an issue. And the reason for this is that actually parameters change. So you may calibrate your model on one period of time, but then you come to another period of time and some things change. They've changed the ventilation system, or they put an extra dehumidifier in, or they've done something, and the model doesn't actually know that unless you tell it. So what we need to do, if we're going to embed our model into our digital twin, we need to know that the model at any moment is actually giving you a good representation of what's actually happening in the real system. So we need to ensure that the physics-based simulation maintains model fidelity as the system changes in time. So if we consider a system that has a step change in value, we have 2 periods, and then we might generate some monitored data over these 2 periods. We can run a Bayesian calibration, which is the approach we like to use. And what that gives you is a probability distribution of the parameter value. And if we can run period 1 and period 2 separately, this will actually give us a good estimate of what the distribution of the probability distribution for parameter 1 and parameter 2 might be for those 2 periods. This is fine so long as we know we've got a change in parameter value. If we don't know, and we inadvertently run the calibration over the whole of period 1 and period 2 together, what we will get out is an average value of the parameter value over period 1 and the parameter value for period 2. So we won't identify that step change in value. And what we will get when we run our model with this is an average, and that's what we're seeing on the slide before. So we've come up with a system to address this, a sequential calibration approach, which uses a particle filter. Just to give you a quick insight into how this works, what we basically do is we set up a large number of particles, so maybe 1,000, where a particle is a set of parameter values for the parameters you're interested in. Each of those you assume has uniform probability, and you look at what the model would give you for those parameters values at that period in time, at that point in time. You then bring in a data point. So this is monitored data. And what you do is you look at the likelihood of each of your particles given your data point. So you look at the probability that any of your particles are actually, how close they are to the true value, given your data point and given the output of your model. There's then a resampling step where you actually resample the same number of particles again based on how likely your particles have been deemed to be, so that you end up with more particles closely spaced together in regions which are deemed to be the most likely. And you can then do that again. So you bring in another data point and you do the same thing again. And you can keep going with this on and on with new data points coming in. And at each time, you're updating your probability of what you think your parameter values are most likely to be. And what you get from this is a sequential probability distribution for your parameter values. And so this is based on the toy problem shown on the previous slide. And you can see that whereas parameter 2 doesn't change over the whole system, parameter 1 actually identifies, we're identifying this step change in value round about here in the middle. And so the particle filter calibration is actually picking up the step change in value. So this is potentially really useful. So let's apply this to the growing underground model. We're interested particularly in internal airspeed and ventilation rate, because these are 2 parameters that are assumed, that are used in the model, and they effectively govern the heat exchange with the outside, because they govern the mass transfer of water from the plants to the internal air and the bulk transfer of that internal air to the outside. So we can run our particle filter calibration over a period of, this is August to October in 2018. What these plots show you on the left-hand side, and the top one is ventilation rate, and the blue solid line is the mean output from our particle filter approach. So this is effectively saying this is the mean value of ventilation rate that gives the best agreement between the model and the data that we're monitoring. And you can see it's quite variable. And on the bottom, you have the internal airspeed that corresponds to that ventilation rate. And so these 2 parameters together can be fed back into the model and should give us a good agreement. Also shown on the top plot is the actual setting on the ventilation system. And there's 2 ventilation systems in the tunnel, one at each end. One of them, so this is the black dotted line. One of them was at a reasonably high level through August, and then at the beginning of September, it was turned down and then stayed constant for the rest of this period. And one of them was relatively constant at the start and then was turned down at the end of sort of midway through September. And I'll be honest, I was really hoping that this particle filter approach would be able to identify this step change in the ventilation system settings. But it quite clearly can't. And with hindsight, it's not that surprising, because in our model, which is quite simple, we have one parameter for ventilation rate that encompasses both the ventilation of the ventilation system, but also all uncontrolled ventilation, so infiltration. And bearing in mind, we've got lift shafts, we've got doors that can be open and shut. There's a lot of uncontrolled ventilation going on as well. So this parameter is actually effectively giving us the combination of all the different sources of ventilation. So as I've said, we can feed these values back into our model. And on the right-hand side, we've done that. So we've got the blue solid line is the mean output of the model given these mean parameter values. And the shaded area is the interquartile range. So as I've said, what we're actually getting is a probability distribution of the parameter value at each data point. The red circles are our monitor data and the black dots are the calibration points. So we've taken 1 point every 12 hours. And you can see that the relative humidity is actually increasing over time from September the 1st up to September the 6th, and then it has a sudden drop on September the 7th. And the output from the particle filter model is actually following that reasonably well. It's not quite getting up to the peak and it's not quite getting down to the bottom, but it is at least giving us that change. We also ran a static calibration just over the first period, and that's shown in green on the left-hand plots. It gave us a value of around 6.5 air changes per hour for the ventilation rate and 0.23 meters per second for the internal airspeed. But you can see that if we use that with our model, exactly the situation we were expecting happens. It doesn't match this change in relative humidity at all. So this approach is working quite well. And if we go back to our slide I showed you originally, this is what we had. We had our simulation not comparing very well with the data over the winter periods. Now it compares really well. So this is a calibrated model, and this is now running the model again and comparing it back against the data. So our aim is to put this into the digital twin. This is what we're doing over this next few months. And what we'll be doing is we'll be taking in monitored relative humidity data. We'll be inferring the ventilation rate and the internal airspeed. And we'll be able to feed that back into the model and see how it compares against the monitored data for temperature and relative humidity. But also we can then start to run scenario evaluations. So for example, we can say, okay, so if we turn the ventilation system up, what impact's that going to have? Or we can try other scenarios as well. Okay, so that's urban integrated farming. That's where we are with that. I'm just going to talk very briefly about what we want to do in the building integrated agriculture field. This is a, sorry, I'll just go back one slide. So when we have building integrated, you'll remember I said right at the beginning that what we're talking about is a fully coupled system. So the plants are then coupled with the air around the plants is coupled with the air around people in the rest of the building. This is a really nice building. This is in Hackney. It's the headquarters of the Seawater Greenhouse Company. They basically built an end terrace on the end of this terrace row of terraced houses. And the top floor of this end terrace is actually a greenhouse. And the idea is that the warm air, which is oxygenated, is fed back down to the bottom of the building. There's a workshop space in the bottom here, and the air percolates back up through the office space on the middle floor, loses its oxygen, picks up some CO2, loses some heat, and cooler CO2 enriched air comes back up to the greenhouse, and then you get this interaction with the plants again. So this is a really nice ideal system. And actually the people who use this building do tell me they have very low heating bills, but they're not quite sure whether that's because of heating from the greenhouse at the top or whether it's because they're actually taking heat out of the next door terrace. So my colleague Melanie has done a simulation study for an archetypal school with a greenhouse in it. So this is, she uses Energy Plus for the building, and she's basically replaced an entire classroom with a greenhouse. And the benefit of this model is you can then run the scenario evaluations, so you can explore the impact of having a greenhouse in this school on the energy demand, on the environmental conditions, and on human comfort. And just to show you some results quite quickly, this shows you the conditions in the greenhouse zone. For the situation, the blue solid line is if you have no plants, and the orange solid line is if you have lots of plants, so a fully planted greenhouse. On the left-hand side, you can see it has a big impact on the carbon dioxide levels, as you might expect. In the middle one, the relative humidity goes up, as you might expect, and we have a small impact on the temperature, showing on the right-hand side, a small drop in temperature as a result of the plants. But as I've said, the real beauty of this is you can perform a scenario evaluation, and Melanie ran something like 350 runs of the entire model over an entire year to do this evaluation of all of these different parameters. So she could look at cooling set points and heating set points in the greenhouse, the planted area, the size of the roof window, the shading levels, and also looking at the interactivity. So how, if you actually mix the air from your greenhouse with the corridor, what happens? If you mix the air in the greenhouse with the classroom below, what happens? And so, for example, if you look at energy demand, this is showing you standardized regression coefficients. So basically, the bigger the box, the more important the parameter. So the cooling set point in the greenhouse is very important from the point of view of the energy demand in the spring and summer, as you might expect. But actually, air mixing from the corridor to the greenhouse is very important in the winter and autumn. And so this can give you real insights into how to design a greenhouse zone within a building like this school. Now, unfortunately, obviously, the situation is we don't have any monitored data for this. So while we can do sense checks and we can, run these scenario evaluations, what would be really, really nice would be to have an actual building with an actual greenhouse and monitored data that we could actually calibrate our model, and then we could really do this in great detail. So hopefully that's coming in the future. So that's all I'm going to say. So I'm hoping there's lots of questions. If you want further information, as I've said, there's a GitHub page with the MATLAB model on. There's a couple of papers, Melanie's paper on the co-simulation work and my paper on the continuous calibration. And also we have a chapter in the book Smart Plant Factory as well. And I must just say a big shout out to all these people who've helped us. So Catherine from University of Warwick, the Alan Turing Institute, particularly the research engineering team, and Growing Underground, who have been fantastic collaborators with us, as I say, for the past 7 or 8 years. Thank you.
Thank you very, very much, Rebecca. This is great talk, quite impressive. I would encourage everyone to raise your hand or put your question in the chat. I can start just to break the ice. So it's really phenomenal to see the level of details that you can extract from those infrastructure and eventually know things that otherwise would be completely unobservable. And so it's quite remarkable. First of all, a generic question. Do you think this is a viable model growing in buildings? So given the demand of London, for example, just to have a bit of scale or context, what is the portion of that demand that is we could forecast in a certain sense to be able to satisfy?
Oh, that's a very good question, actually, and I don't have any figures to hand. I think it's one of the interesting things, obviously Growing Underground are growing microsalads, which are very popular and they're used a lot in restaurants and they sell to supermarkets across London. But at the end of the day, they're salad crops and, we can't only live on salad crops, obviously. So they're actually expanding into a warehouse plant factory, hopefully soon. And I think they're going to be exploring growing different types of crops, because I think to actually really, feed a lot of people, I think you're going to have to be growing more than just salad crops, is my feeling. I don't really, as I say, I don't really have the numbers in terms of London, for example. Yeah, that is a very good question, and it's something we should.
Or for example, of the 3 topologies that you have shown us, what do you think is the most promising, the most efficient, for example? I think
the most efficient is the plant factory, actually. I think that is, and I think that's an increasingly developed technology as well. There's a lot of the plant factory work in Japan and in the Netherlands and coming in the UK and in the States. So, and that is really efficient because you don't have to pander to anybody else. You can actually create a perfect growing environment for your plants. It's sort of disconnected from its environment, but actually in the middle of a city quite happily. If you can put a warehouse in the city, you can actually put a plant factory in the city. So I think that is actually the most promising technology. But then that doesn't do anything for health and well-being, for example. And there are benefits for putting greenhouses in hospitals or in schools particularly, which although they may not be major crop growers in terms of feeding the wider community, they would feed the hospital or they would feed the school, and would have the benefit of people being able to visit them and being able to experience the pleasure of actually being around plants growing, as well as, so they would be multi-purpose in that environment.
But in fact, it's very poetic to think also at this setup in which you have human and plants together. But would that be compatible? So the climate that we need, the regulated climate of people that we need, 20 degrees, nice humidity, and a cozy environment, would be fine for the plants? Or do we need to somehow share that and reach a compromise between humans and plants?
I think they would, if you wanted to have the plants growing in amongst the people, or the people in amongst the growing plants, sort of, as opposed to having a separate greenhouse within the building. Obviously, a separate greenhouse within the building has the benefit that you can please the plants and you can improve your crop yield. If you actually, and people could visit a greenhouse and then they could put up with the fact that it was quite warm, so they wouldn't, whereas if you actually wanted to grow the plants in amongst the people, then yes, you would have to accept a lower crop because you wouldn't be able to generate the two are slightly incompatible. It would have to be too hot, or too cold for too cold for the plants, or too warm for the people. So it is a compromise to actually do both together. But there could be, if you could actually quantify the benefit of having plants growing around, the benefit of house plants, the benefit of crops growing around you, in terms of to your health and well-being, then you could offset that against the lower crop yield. So, but it's how you would quantify that as a benefit, I don't know. That's a very tricky question.
Thank you. Simon or Simone, would you please speak? You have a question, otherwise I will read your question, but if you can, please feel free to step in.
Hi, very nice talk. I was just wondering, one, you mentioned something about being difficult to characterize the moisture exchange from plants, and I did think that why is it that difficult to characterize?
It's difficult because it's difficult in growing underground because we're growing microsalids, and there's really not been very much research done on plant transpiration rates in the first 10 days of growth. So we're really talking plants that grow over a period of week to 10 days. So they are literally quite small plants when they're harvested. And so whereas when we worked at Kew, there was quite a lot of work had been done on tropical plants and transpiration rates for tropical plants. And what you're really trying to do, what you really need to do is to characterize this this resistance term, so the stomatal resistance, and trying to find a value for that parameter for the microgreens is, well, it just doesn't exist, to be perfectly honest. So that's why we're relying on values for lettuce. But even the values for lettuce are typically measured once the lettuces have actually reached a sort of a reasonable size. So you're extrapolating down below the size of the plants have grown. And I think to measure it, I think I'm right in saying that the tools, I'm a bit hazy on this because I'm not a plant scientist, but I understand that the equipment you need to measure transpiration rates is actually quite, works better for bigger leaves, I believe. And hopefully somebody might jump in and correct me if I'm wrong here. But so I've not as yet managed to successfully actually measure it. Plus the fact in growing underground, they grow about 7 or 8 different crop types. So you'd have to do it for each one, and they're all different. So it's just, it's tricky. It's easier to do for a greenhouse where you're growing tomatoes, because there's lots of greenhouse models for tomato crops or chili peppers or something like that, where they grow quite big, and they're a very financially important crop. So there's been a lot of research into how you actually simulate the growth of a tomato plant, for example.
Thank you.
Other questions? I have a curious, yeah?
Can I,
Please,
have a question? Yes. So one of the challenges in indoor urban agriculture like this is the cost aspect, right? It's usually, as long as I know, it's like a 3 times, 4 times more costly compared to conventional outdoor planting. And actually, your the digital twin models and all this data is really, really interesting to understand where is this cost coming from, and whether it's ever possible to reduce down cost in theory and in practice. Have you thought of this aspect in your project? And do you have any ideas to what extent we can reduce down the cost in the future if we do whatever?
Yeah, sure. I mean, I think, so there's 2 aspects to cost. There's obviously the capital cost in building the system in the first place. But I think we're more talking about the ongoing costs. And obviously, when you're growing, when you're not making use of solar radiation, you have to have grow lights. And so certainly for growing underground, I think the biggest cost for them is the electricity consumption associated with powering the lighting system. And the ventilation system. Now, yes, it is costly. It's a difficult one, because obviously growing underground is a profitable farm, so they've managed to make it work. And actually, when you look at their yields, they actually yield far better than a greenhouse. So I don't quite see why the cost is such a barrier, because it definitely does seem to be working for them. So I'm not quite sure. It's not something I've personally looked at, because I'm much more on the physics side of the actual physical side of what's happening. But it certainly would be an interesting study going forwards. I mean, and also not just the cost, but also looking at what Fulvio was saying. His question was it's more of a cost benefit analysis in the center of a city of what you can grow, how much you can grow, how much that will support the local community, and what the cost implications of actually getting it up and running and getting it profitable would be. So I'm sorry, that's a fairly vague answer to your question, but I don't unfortunately have the numbers to answer.
It's a very interesting question and discussion here, because intuitively, if we do it outdoor, we get the ventilation and the sunlight for free, right?
Yeah, exactly.
But here we have to provide everything. So that's the kind of inevitable negative aspect of this. But on the other hand, you can reduce down probably the amount of work you need outside, and the manpower is much less, and perhaps and then the yield is probably much higher than outside. So it's going to be a kind of the balance in the end. So is this kind of intuitive understanding the whole balance is correct, or do you have a different impression of the whole thing?
No, I think that is my impression. It's very much a balance, I think, and I think it takes a long time to actually fully understand the way that different things, different factors impact on that balance. For example, you mentioned reduced staffing, which is true, and that obviously robotics will play an important part, particularly if we move to plant factories. Robotics, I'm sure, will be a really important part of that. And okay, there'll be, again, a capital cost in setting that up, but then you can offset that against reduced staffing costs potentially. So I think it is very much a balance, and I don't think it takes much for that balance to tip the wrong way, because I know there's been a few rooftop greenhouses worldwide that have not been profitable for whatever reason, and so it clearly is. It is finding the right balance and finding that way to make it profitable so that it can actually work is quite hard, I think.
Another aspect of this is probably the quality of each individual crop. Like if we can have a better quality, maybe we can, consumer can pay more. Is this actually something you can observe from your experience so far?
Yeah, I tell you, the crops that growing underground are amazing. They taste fantastic because they're harvested and to the consumer really quickly, because they're in the centre of London. They grow wasabi shoots, which are just incredible. So I'm a big fan. So yeah.
There is a question from Elliot Dixon. Please, Elliot, speak out.
Yeah, hi. Thank you very much for that talk. Interesting concept I've never come across before, to be honest. Do you think that your model and having a model there of the specific building would help you detect any potential issues going on the farm before they really impact the growth? For example, a failure in the ventilation system has not been caught by the ventilation system itself, and alert that to the farmer.
Certainly, we would hope so. That's definitely the direction we're going in, and I think in a system which is more purposefully designed to work that way, then a model could quite reasonably easily pick up when something is actually not behaving the way it should do. And so alert. So for example, the lights don't come on, and then the model, to be honest, the data will actually pick up if the lights haven't come on. But it certainly, you could use the model to, as I said, this calibration approach will pick up a change in parameter value. So there's definitely scope for developing the model in a way that you could actually calibrate for something rather than the ventilation rate and the internal airspeed. You could actually calibrate for a different parameter that might be more critical. I'm hypothesizing now, but it could definitely be done. And one of the issues we found was that if the data were very noisy, so if there was a lot of measurement error in the data, then the model will find it harder to actually pinpoint a change in parameter value. So you need to have good data, and the model needs to be able to track that quite accurately. But we've done, as I say, one calibration approach here. We've used data every 12 hours to do the calibration. If we use data every 4 hours, we might get a better result. So there's a lot of development to be done. But I think certainly this type of modelling could be used to actually find faults. And you could also use statistical modelling because we've got so much data. I know Melanie's developed forecasting models for forecasting temperature, but you could actually use the data itself depending on what it is you're wanting to find the faults in, if you see what I mean. So, but you could be using the data, and actually that could be flagging up something not actually being as it should be. But to be honest, the data are the key. If you can get some good data and accurately monitored data, then that is really, really useful and can give you lots of insight into what's going on. And one of the challenges with growing underground is that because it's built in effectively a derelict space or a disused space, not very much is purpose designed for the farm. So for example, the ventilation system was the ventilation system designed for the tunnels when they were built as air raid shelters. So it's not the ventilation system you would design if you were designing a farm to be built underground. So lots of things, there are things like that you could do much better if you started from scratch and actually designed a system. But that's not to take anything away from what Growing Underground have done, because they've got this fantastic facility now. And in many ways they've succeeded despite these challenges. But modelling definitely helps, I think. I would say that, but because I'm a fan of modelling, but yeah.
Very, very last question. Carbon emissions, are they a big unknown, a big issue? The intuition is carbon emissions are higher, but maybe this is not true. How do we handle that?
Yeah, that's a really good question. Obviously, you're using a lot of electricity to power your lights. So there are carbon emissions associated with that. And there's very little, the lights generate the heat, so there's no heat input going in, but that is obviously a big impact. So as I said, Growing Underground they're a carbon neutral plus organisation. So they get all of their electricity from renewable sources and are looking to, they're also offsetting some of their emissions as well. And they're looking at the best ways of doing that. They're using an approach at the moment, but I believe they're looking at different approaches. One of the things, I mean, obviously you could be doing things like putting solar panels on the roof. You could be generating your own electricity because you're not having to, particularly if you have a plant factory, which is in a warehouse, then there's nothing to stop you doing something with your roof space like that. And I suppose when you actually take the system as a whole overall, and you consider the fact that you're actually growing in the heart of the city, so that's reducing the carbon emissions on the journey from the farm to the table. And so you need to consider that as a whole as well. But yes, obviously carbon emissions are important and they do need to be negated in as best as way as possible.
Very good, very good. Thank you very much, Rebecca. This has been really an education. And with that, I think we are up to our time.
Okay.
Thank you for everybody for attending. And I remember you that there will be another seminar the 18th of June with Elliot Dixon from Agri Epicenter. And with that, we close the session. Thank you very much and have a good weekend to everybody.